Hello everyone, I'm Ryan Shalom, PhD student at Frere Mansouri University from Algeria. I'm here today to talk about COVID-19 detection from chest X-ray images using deep CNN architectures with the transfer learning. First, I would like to tell you about why we are interested in automatic COVID-19 detection and classification. Second, I will describe the methodology applied. Then I will discuss our results. And finally, I will give you a brief conclusions and a future works. We start by introducing our works. The novel coronavirus appears in Wuhan province in China in December 2019. It is named as COVID-19. It outbreaks rapidly over the worldwide and becomes a serious public health pandemic. COVID-19 is the third in coronavirus family. The first coronavirus epidemic is the severe acute respiratory syndrome coronavirus. It was recognized in China in 2002. The Middle East respiratory syndrome coronavirus is the second one. It was started in Saudi Arabia in 2012. Coronavirus epidemic or COVID-19 is transmitted from person to person through the breath, cough, and contact that caused rapid and widespread of the epidemic. As shown in the figure, the number of coronavirus cases worldwide is increasing since January 2020. COVID-19 causes respiratory tract infection, pneumonia, fever, dry cough, and tiredness. Patients with COVID-19 might be contagious despite being clinically preserved and having multiple negative throat swabs. Early recognition of suspected patients allows for timely initiation of infection preventions and control. Reverse-transcription polymerase chain reaction testing is the most efficient screening methods of COVID-19. Patients with COVID-19 or with positive RT-PCR must be isolated from public and take their treatment. However, the increasing of infected cases led to the increasing demand of the screening RT-PCR, which depends on the availability of testing kits. RT-PCR kits are expensive and cannot be afforded by all persons. RT-PCR testing results will be obtainable in few hours or day to 2 days in developed countries and can take more than a week in third world countries. So, what are the faster techniques that could reduce the number of RT-PCR kits used per day? COVID-19 epidemic affects lung and classified as pneumonia disease. One of the proposed methods that can be used as primary test of COVID-19 is chest X-ray images classification. Radiologist experts use chest X-ray images to detect the damage caused the COVID-19 into the lungs. They extract the characteristics from chest X-ray images to detect COVID-19 and interpret them manually. However, manual detection takes an important time and depends on the radiologist's expertise. Also, the tiredness of experts influences to their decision and increases the error rate. Therefore, it's important to implement an automatic detection and classification system of pneumonia and COVID-19 disease to save time and reduce radiologists' interventions. Deep learning methods, in particular convolutional neural networks, are often used for pneumonia disease detection and classification using chest X-ray images. The number of chest X-ray images containing COVID-19 is limited, and the number of training data sets is very small. So, what is the good combination to solve manual classification and data sets limitation problem? We propose an automatic classification system which combines between convolutional neural networks and transfer learning for three types of chest X-ray: normal, pneumonia, and COVID-19. We used COVID-19 datasets from GitHub, pneumonia and normal from Kaggle. We adopt deep transfer learning for feature extraction from chest X-ray images using two deep CNN architectures, AlexNet and Residual Networks ResNet50. We also use tenfold cross-validation methods. We pass to describe our methods starting by the datasets. For our experiments, we use two different public datasets. The two datasets contain chest X-ray images. The COVID-19 datasets is collected from hospitals. Some images are collected indirectly from publication and websites. The datasets contain different types of pneumonia chest X-ray images. In our experiments, we used only COVID-19 images from these datasets. At the time of writing, it comprises 551 images. Chest X-ray datasets contains different three types of labels: normal, bacterial pneumonia, and viral pneumonia. The splitting of data into train and test sets is performed on slice basis. As shown in the figure, 80% of images are used for training and 20% are used for test. The table represents the distribution of images among the different types of infections and the number of images used for training and test for each type. We pass to present deep transfer learning architectures. Transfer learning research focuses to solve one problem and applying it to solve different related problems. In our work, we used the two CNNs architecture AlexNet and ResNet50 trained on the ImageNet dataset with 1,000 categories to solve pneumonia disease detection and classification problems with three categories. We take the pre-trained AlexNet and ResNet50 and applied them to learn different infections of pneumonia diseases, COVID-19, normal, and pneumonia, using a small number of training images. Now we pass to the preprocessing. In our work, the preprocessing is divided in two steps. First, we convert the gray chest X-ray images into RGB images to adapt them to the existing pre-trained architecture used in our experiment. Then we resize them into 224 by 224 RGB images for the reason that we are limited by the memory constraints. Now we will talk about the training parameters that we have chosen in our work. The networks are trained by stochastic gradient descents with the following parameters: momentum of 0.9, epochs number of 100, the mini batch size of 128, the weight learn rate factor of 10, and bias learn rate factor of 10. In this part, we will describe the equation used to calculate the performance metrics. In order to perform the transfer learning, we choose k-false as a cross-validation method. The equations from 1 to 5 are used to calculate the performance metrics of our network for one fault. TP, FP, TN, and FN are the number of true positive, false positive, true negative, and false negative, respectively. The total performance matrix is the average of performance metrics. It is calculated using the equations from 6 to 10. We calculated the average accuracy, the average recall, the average specificity, the average precision, and the average F1 score. Now I will discuss our results. We implement our two different pre-trained networks that are AlexNet and ResNet 50 using MATLAB 2019 version B. The main goal of our research is to increase the classification performance metrics of COVID-19, combining between CNN, transfer learning using small number of data, and tenfold cross-validation methods. To evaluate the classification performance, we used two criteria: the classification performance matrix and the confusion matrix. As shown in the table, the classification performance of ResNet 50 is better than AlexNet. All the performance metrics obtained using ResNet 50 are greater than the performance metrics obtained using AlexNet. The mean classification accuracy obtained using ResNet 50 model achieved 99.25%. However, we achieved 96.74% of mean classification accuracy using AlexNet model. Also, the mean recall, mean specificity, mean precision, and mean F1 score obtained using ResNet 50 model are better than those obtained using AlexNet model. Here is the confusion matrix for AlexNet and the confusion matrix for ResNet 50. It can be observed that the number of COVID-19 images is limited compared to normal and pneumonia images in the two confusion matrix. The confusion matrix for AlexNet shows that 9 patients with COVID-19 is misidentified as normal and 5 are misidentified as having pneumonia disease. Also, 2 pneumonia patients are misidentified as normal and 7 patients are misidentified as having COVID-19. The confusion matrix for ResNet 50 shows that 1 patient with COVID-19 is misidentified as normal and 2 are misidentified as having pneumonia disease. Also, 1 pneumonia patient is misidentified as normal and 2 are misidentified as having COVID-19. The table provides a comparison between the model used in our works and the existing methods on the same COVID-19 and chest X-ray datasets. It can be observed that our proposed shows the best classification accuracy compared to the previous works, with the 99.25% of classification accuracy. That brings me to the end of the presentation, so just to recap. We proposed an automatic system for COVID-19, normal and pneumonia disease classification from 2 available public datasets. Our system is the faster techniques that could reduce the number of RT-PCR kits used per day. Our system applied the concept of deep transfer learning using 3 pre-trained architecture and tenfold cross-validation methods for chest X-ray images classification, trained for 100 epochs using small number of data. Our system outperforms the classification accuracy compared to the raised works. For future works, we increase the number of COVID-19 and pneumonia and normal images in the chest X-ray images, and we will develop an automatic computer-aided diagnosis for COVID-19 detections. Thanks for your attention and I will be very excited to answer all your questions.